In 1984, three researchers at MIT Sulzer, Reed, and Clark published a paper that became one of the most cited in computer systems. Their insight, called the end-to-end argument, states, the function in question can be completely and correctly be implemented only with the knowledge and help of the application standing at the endpoints of the communication system. Here's what that means in practice. TCP retransmits lost packets. It guarantees that every packet arrives in order, exactly once, from the perspective of the TCP stack. This is excellent. But it cannot prevent a user from submitting a duplicate HTTP post request if their browser retried after a network timeout. The TCP layer has no idea that two separate HTTP requests represent the same user intention. Only the application, sitting at the endpoint, knows that. TCP did its job perfectly. The application still has a duplicate problem. The end-to-end argument applies equally to databases. Just because your application uses serializable transactions, the strongest isolation level, does not mean it is free from data corruption. If the application has a bug that writes incorrect data, serializable transactions are not going to save you. They faithfully execute the incorrect write exactly once. The application itself must take end-to-end measures. Kleppmann's example 12:1 is instructive. A money transfer transaction update account set balance equals balance plus 11.00 where account underscore ID equals 1234, update account set balance equals balance 11.00 where account underscore ID equals 4321 is not idempotent. If the client sends it, receives no response due to a network interruption, and retries, the transfer executes twice. $22 are transferred instead of 11. And real banks do not work this way. The solution is operation identifiers. Generate a UUID for the transfer request. Store it in a requests table with a unique constraint on request underscore ID. Include the request ID in the insert. If the same request arrives twice, the second insert violates the unique constraint and the transaction aborts. The retry is safe. This is end-to-end duplicate suppression. It flows from the browser client all the way through to the database, crossing every layer. Uniqueness constraints are the simplest correctness requirement. No two users can have the same username. In a single-node system, this is trivial: one database, one serializable check. In a partitioned, distributed system, it becomes hard. Enforcing a uniqueness constraint across partitions requires consensus. The system must decide which of several conflicting concurrent operations wins. The classic approach is to route everything through a single leader. One node is in charge, all requests funnel through it, it decides the ordering. This works fine as long as the leader doesn't fail and as long as you don't mind the latency of routing every request through a single node, potentially on the other side of the world. Kleppmann shows how the unbundled, log-based approach handles this. Here's the algorithm for claiming a username. First, every request for a username is encoded as a message, appended to a partition determined by the hash of the username. All requests for Alice go to the same partition. Second, a stream processor sequentially reads the messages in that partition, single-threaded, in order. For every request for an available username, it records the name as taken and emits a success message. For every request for an already taken username, it emits a rejection. Third, the client watches the output stream for a success or rejection message corresponding to its request. This is isomorphic to linearizable storage using total order broadcast. It scales by increasing the number of partitions. Each partition handles its own username namespace independently, so throughput scales linearly. The key insight: the log gives you a single, ordered sequence of events for each partition. That ordering is sufficient to resolve all conflicts deterministically. But here's a liberating observation: many applications can actually get away with loosely interpreted constraints. If two users concurrently book the same seat on a flight, the system can accept both, then send one of them an apology and offer an upgrade. Airlines routinely overbook in the expectation that some passengers will miss their flight. The cost of the apology is acceptable. In that case, a linearizable uniqueness constraint is unnecessarily expensive. Write optimistically, check after the fact, compensate if violated. Integrity without synchronous coordination. Kleppmann makes a distinction that's easy to overlook but profoundly clarifying. The word consistency is used in databases to mean at least 5 different things, and 2 of those things are worth separating carefully: timeliness and integrity. Timeliness means ensuring that users see an up-to-date state. If you read from a follower replica that is slightly behind the leader, you might see stale data. The user who just updated their profile photo still sees the old one. This is a timeliness violation. It is temporary. Wait a few seconds and try again, the replica will catch up. Integrity means absence of corruption, no data loss, no contradictory data. If a database index is missing some records, if it doesn't correctly reflect the contents of the table, that index is broken. If a money transfer deducted from one account but never credited to another, money has vanished. That's an integrity violation. Waiting and trying again does not fix it. Kleppmann's slogan, violations of timeliness are eventual consistency. Violations of integrity are perpetual inconsistency. The first is annoying. The second is catastrophic. His example, your credit card statement. It is completely normal if a transaction you made within the last 24 hours does not yet appear. Banks reconcile and settle transactions asynchronously, we all know this, and timeliness is not important here. But it would be very bad if the statement balance was not equal to the sum of the transactions plus the previous statement balance. That would be an integrity violation. The practical implication for distributed systems design, integrity is much more important than timeliness, and integrity does not require distributed transactions. The mechanisms for maintaining integrity in an event-driven system are, representing each write operation as a single atomic message, fits naturally with event sourcing, deriving all other state updates from that message using deterministic derivation functions, passing a client-generated request ID through all levels of processing to enable end-to-end duplicate suppression, and making messages immutable so derived data can be reprocessed. This combination achieves integrity without the coordination overhead of two-phase commit. All our reasoning about fault tolerance rests on system models, sets of assumptions about what can and cannot go wrong. We assume processes can crash. We assume networks can drop messages. But we typically assume that data written to disk is not lost after FSINC, that data in memory is not corrupted, and that the multiplication instruction in our CPU always returns the correct result. These assumptions are reasonable. Most of the time they hold. But they are probabilistic, not absolute. HDFS and Amazon S3 do not fully trust disks, they run background processes that continually read back files, compare them to other replicas, and move files to mitigate silent corruption. The reason, if you have enough disks running long enough, even very unlikely events happen. Hardware faults, radiation, certain pathological memory access patterns, all can flip bits in memory with no fault detected by standard checksums. The technique known as Rowhammer exploits memory cell interference to flip bits in memory locations that have no hardware faults. Once you look closely, hardware isn't the perfect abstraction it seems. Software bugs are equally treacherous. Kleppmann reports personally seeing cases of MySQL failing to correctly maintain a uniqueness constraint, and PostgreSQL's serializable isolation level exhibiting write skew anomalies in well-regarded, battle-tested databases used by millions of people for many years. The solution is not paranoia. The solution is auditing. Financial systems have understood this for centuries. Double-entry bookkeeping is a self-check. Every debit has a corresponding credit. If the books don't balance, something is wrong, find it. The design principle is not to trust that everything is working, but to continuously verify. Event sourcing architectures have a natural advantage here. The derivation of state from the event log is deterministic and repeatable. You can rerun the batch and stream processors that derive to view and check whether you get the same result. You can use cryptographic hashing to verify the event log has not been tampered with. Cryptocurrencies and blockchains have popularized Merkle trees, trees of hashes that prove a record appears in a dataset, and certificate transparency uses Merkle trees to audit the validity of TLS/SSL certificates. These integrity checking ideas will likely find their way into mainstream data systems. The future belongs to self-validating, self-auditing systems that continually check their own integrity rather than relying on blind trust.